Okay, I felt like I should supplement this track 10 because we're down here. If you can see that on your screen recording, we're down here on track 10. This is going to be track 10B. I didn't do this for my backyard physics students, so I'm going to add this little piece because I added some slides to your slides on the Magnus Force. So let's take a look at those now. That's what we're doing here. So this is a little pause in the action so you can see what a Magnus Force actually is. All right. So here we go. Air pressure on moving objects is what we're doing here. So let's just go ahead and go to the slideshow. It's not bad. All right. So here's why does a curveball curve? All right. Direction of airflow over the ball. We find out through the Bernoulli effect, fast-moving air has less pressure than slow-moving air. Okay, fast-moving air has less pressure than slow-moving air. So, when the air going underneath the ball has a lot more, or the low pressures over here, and because of the spin of the ball, it causes, since this is lower, it's going to cause this ball to curve. All right, so here it is. No spin. No spin. This is like a knuckleball, but it actually, knuckleballs, as you saw on those one videos of knuckleballs, they kind of go all over the place. The Kawanda effect, we call that Bernoulli. I call it the Bernoulli force. Okay, so here's the airflow. Now look, here's the Magnus Force spinning. We're looking at the top view here. Looking at the top view, airflow is causing spin, less pressure over here, or less pressure here on top, more pressure here on the bottom, causes a force this way, okay, which causes it to curve. And here's a basketball. If you took a 5,000 frames a minute type or 100 frames a second type picture, you get this, and you can see that it bends out. It actually curves when it's coming down. Okay, in soccer, just as for a baseball and a basketball, a soccer ball will veer off an unexpected trajectory. For soccer ball or basketball, the Magnus Force is this. This looks complicated. Your Magnus Force for the boomerang will be a little bit trickier. Okay, so here's the Magnus Force where C, Magnus Force, coefficient of drag. Well, that's the coefficient of the Magnus Force in this case. And for a soccer ball, I think it's 2. P is the density of air is 1.20. I like to use 1.29 myself, or 1.3. D is the diameter of the ball. Spin rate, how fast it's spinning, the frequency of its spin, and the velocity. Okay, and so you will do one for a baseball, right? Which will have the exact same thing. So you bend it like Beckham. So the initial velocity is 25 meters per second in this direction, going this way, and it bends. Okay, and right after this, you've got several of the famous kicks in soccer. So 10 revolutions per second. So that's what it looked like. Magnus Force about 3.9 newtons. How does this compare to the weight of the ball? The soccer ball has a mass of 0.43 kilograms. The weight would be m times 9.8. So it's 4. So it's equal. Is almost as strong as gravity and will cause the ball to bend by 4.6 meters. Right? Won't keep it from falling, but it will make it bend about 4.6 meters. That's amazing. Okay. And so that's what we're going to find out is the radius of spin. All right, so the rest of this, we're going to be using this equation up here, 4I. Now I've got to explain what that equation is, and I do that in the next few videos. All right, but enjoy watching the great soccer kicks. And so I just wanted to add this little supplemental video here. We are done with this one.